Welcome back. This lecture is um, collation of many experimental results which we have presented in the last few lectures. Why is this important? Because we would be discussing two models for nucleus, and if the models have to have some credibility, they should be able to explain, rationalize these experimental results. That is why we are just putting together all the important experimental results. That also tells you what a nucleus is. So it's good to see all these results together. So before we get started, I want to also differentiate two kinds of models. So there is the first kind of model, which is often called, let's say, first principle model. So here, the nature of Hamiltonian or interactions are well known. So we can write the equations of motion very clearly. So it's easy to discuss these things with an example. For example, if you consider oscillation of a pendulum, we know the nature of the equation of motion, the nature of forces that are acting. Let's say just a gravity, if you have a spherical pendulum, you have tension acting on the pendulum and so on. You may have air drag, but you may neglect it and then predict something. Okay, so you can write the equations of motion and come up with a prediction. Okay, so this is one kind of model. In these kinds of models are also present in quantum mechanics, wherein the Hamiltonian is well known. You propose the operator for kinetic energy, the nature of interactions. Many a times it is just Coulomb forces, if you're thinking about electronic structure of atoms. Those things are well known. You can also write a model, come up with predictions. So, in contrast to that, you have something called phenomenological model. Okay, it is based on trends and phenomena, and you use a part of experimental data to predict something else. So, in my opinion, one of the best phenomenological model is the model of the periodic table. Okay, how Mendeleev came up with a model of periodic table, or even just the shell model of atom, is a power of these kinds of models. So Mendeleev, if you remember, you might have been told that he predicted based on patterns and reactivity, there were gaps in the periodic table. He even predicted that new elements would be found, right? So shell model of atoms, we know the behavior of elements. That is, atomic number increases, atomic weight increases. Some are less reactive, some are more reactive. Based on that, we can build up some models. Okay, so it need not even be mathematical. Okay, so but you can also have phenomenal fit. So the way to think about this is phenomenological. Okay, so based on a phenomena, you propose what is a logical model. Okay, so that's one way to think about this. The models which we are going to be looking at are mostly of this nature. We'll see why, because a nucleus is a complicated object. It's a many body problem. Okay, so which has complicated interaction. The Coulomb interaction to an extent is known, well understood, but the strong nuclear forces uh, is not that well known. So a nucleus has both these interactions. So to predict the properties of nucleus is not a trivial task, but we will see how such models are built in the context of nuclear science. So it's a great achievement to build such models. We'll see how it is built. We'll start the exact model description in the next class, but in this lecture, we are just collating together all the important experimental observations which we have presented in the last few lectures. So the density of the nucleus is constant and differs only at the surface, right? So this is obtained from scattering experiments. We have presented this. We also presented that the average binding energy is almost constant, okay? But there is a trend. So how do you find? we can find the average binding energy by knowing masses, right? Because mass and energy are equivalent, and mass spectroscopy is a very important um, uh, experimental approach to getting to masses from the mass of protons and neutrons and the nucleus. You can obtain the average binding energy. That's an important experimental feature that has to be uh, correctly described by a model proposed. So if you take a series of isobars, so as the neutron and number of proton vary, the propensity for beta decay also changes. A model has to predict that. As you keep increasing atomic weight and atomic number, uh, there is a certain propensity for alpha decay. The model has to predict that. Um, by adding a neutron, uh, for example, this uh, nuclei will fission. Why so? You should be able to describe that. So, besides a particular atomic weight, an atomic number, nucleides do not exist naturally. Uh, there's an important feature. So, the spin quantum number of the nucleus has a dependence on the nuclear configuration, whether it is odd number of neutron proton or even number of neutron proton. These have to be um, taken into account to build a model. Mirror nuclei. What do you mean by mirror nuclei? Suppose all the neutrons in the nuclei are replaced by protons, and all the protons in the nuclei are replaced by neutrons. So that is the way you build a mirror nuclei. Okay, if you have, let's say, 7 neutrons and 8 protons, you build a mirror nuclei by 7 protons and 8 neutrons. Okay, so 7 8 becomes 8 7. Okay, so that is the way. And when you build a mirror nuclei, it has the same same magnetic, quantum numbers, which we have talked about in the uh, previous lecture. What you go and refer to what you mean by this quantum number I. Magnetic moments are related to I alone, and as the A and Z increases or changes, there are trends in electric quadrupole moment, right? So from a nucleus being spherical, uh, there is a change or deviation from spherical nucleus. The extent of deviation is quantified by uh, electric quadrupole moment. That has to be rationalized. Again, there are trends in isomers. They have the same uh, A and Z, but um, different lifetimes. That has to be rationalized. So this is more a quantum mechanical feature. We won't go into this. At least the underlying basis will not be explained, but we'll touch upon this aspect also. How parity is related to beta decay. Uh, we saw the trends in separation energies, even odd behavior, and suddenly there is discontinuity in binding energy. A good model should be able to explain this important feature. And certain nucleus, okay, are very stable. These are called magic numbers. Why is the stability more for certain uh, kind of uh, nuclear configuration? That has to be explained. And many um, 4n, 4n plus 2, we saw different nuclear chains. They seem to end up with same products. We should be able to explain that. If you have, um, say, at different nuclei with the same number of protons, same number of neutrons, but different number of protons, the trends in stability should be rationalized. Certain nuclei has a greater capacity for capturing neutron. Okay, so that's called, a technical jargon is neutron capture cross section. Okay, this is cross section is synonymous with uh, uh, feasibility of a reaction. Okay, so trends in feasibility of the reaction involving a neutron capturing a neutron has to be rationalized. So the excited states of a nuclei, there is some spacing. That spacing becomes increasingly, it becomes less and less as you go to more and more higher and higher excited states. So that has to also be rationalized. So again, all these things are also elaborated here. So I've quickly gone through this. Pause for a moment to make sure that you recall what we are referring to, what experimental feature we are referring to. Um, so we will present two main models. In the next lecture, we will introduce one of the important model called liquid drop model. That's the topic for the next lecture. Thank you.